Whatever the design, Infineon offers safe choice, easy design in, and reliable performance under various application conditions. We make these key requirements for our MOSFET product development. What does it take to ensure?
Ease of use and easy to design in are key features for the customer, especially for the customers of the mass market, because they do not want to optimize their design for a dedicated MOSFET. We at Infineon have a long history in optimizing our FETs, especially to provide ease of use functionality. Either we do this by design or by the technology, or also by the package, and we see that we have meanwhile all the critical issues like overshoot and induced turn-on, which typically happens in applications, under control.
As a trusted advisor, Infineon puts the success of its customers in the center of its product development.
To ensure a competitive advantage for the customer, we need to differentiate with the MOSFET technology. Our MOSFETs are designed to operate at a very high switching frequency and at a very high current at the same time. So that means we provide a very high power density. And this gives the customer the ability to reduce the form factor and to have less cost in the application.
We are part of today, and we are committed to remaining a part of tomorrow, also with our MOSFETs. So what does the future hold?
Here I see two directions. The first direction goes towards another shrink. That means we go from lateral trench concept to harvesting into the third dimension. We also call it needle concept. And the other direction is go towards more integration. Provide additional features to the customer to differentiate, like a current sense, a temperature sense, or diodes. All in all, I see that our silicon MOSFET roadmap is very well stuffed.
Infineon, part of your life, part of tomorrow.
Good evening to all. Myself, Syam Kamal. And in today's discussion, I'm going to talk about arbitrary time stability and stabilization. Okay, before I'm going to start my talk, first, I like to thank the all organizer of this particular event, because organizing any event is very, very difficult task. And I also like to thank Tak for giving this nice opportunity such that I am able to connect with very, very young mind. Okay. And I hope that at the end of this talk, you are able to familiar with this new concept. Actually, this concept is coined by our group, that is called arbitrary time stability and stabilization. Okay. Similar kind of concept is also existing, and that is called predefined or prescribed time stability. Okay. But this concept is a little bit different than prescribed time stability. I will tell you after the end of this talk. Okay. And I am also going to extend this particular notion for the uncertain system with help of the on-off control, or in more broader sense, using sliding mode control. Okay. So what is the structure of my talk? I am going to talk about the stability. So I will start from the basic idea of stability, how basically stability is derived from the calculus. And after that, how to talk about asymptotic stability, finite time stability, fixed time stability, and then arbitrary time stability. I am also going to talk about some limitations of all different kind of stability. And obviously, whatever things I am going to talk today, that is applicable for several practical systems, especially when there is heavy uncertainty condition. Okay, it means that whatever input channel, that is also uncertain, and whatever our system, that is obviously that is uncertain. Okay, and I am going to collect several examples from robotics, electrical motor design, several kind of targeting and tracking problems, avionics, signal and image processing. Okay, so I will collect few examples. Obviously, in this particular talk, I'm going to limit myself on very, very popular examples only. But after understanding this lecture, you can able to extend this result for your research work. Okay, so let us start the today's lecture. So first of all, what is main objective of the control system? We have certain kind of physical system, okay? And what we have to do, we have to design some kind of feedback or feed forward control such that meet with the given objective, okay? So here in this slide, you are able to see the physical system. This is underwater vehicle, okay? And whenever I have some physical system, always we are specifying the objective, okay? So I'm going to talk about objective of this particular problem. So I want to move this underwater vehicle only in one direction, okay? Or you can tell in a straight line, okay? Because I have to explain some concept, due to that reason, I have kept this kind of simple assumption, okay? So what happens that whenever you are trying to design the control system, either what you can do, you can start from the experiment. You can actually take some underwater vehicle, you can connect all component, and after that you can do experiment. But that is very, very expensive process. Sometimes that is also dangerous, okay? Sometimes whenever we are trying to do something, this system is not available to us. And due to that reason, I need some kind of another platform that is called mathematical platform, okay? So what basically mathematics helps here, that they are going to give us some kind of abstract platform where we are telling that this system can be represented by some kind of mathematical equation. And that mathematical equation is simple for the control point of view. Okay, obviously that should be not simpler. Okay, so you can see here that I have underwater vehicle. So this is physical system. Now I am telling this is the abstract system. Okay, and what I am assuming here, that this particular underwater vehicle is moving in one direction. Okay, and here I have to just control the velocity. I am not worrying about the position. So these are the objective. What is our basic objective? I have to maintain some velocity Vd. Vd might be varying with respect to time or might be constant. Okay, so I have flow of water, and somewhere in between I have to stop that underwater vehicle. Okay, so that kind of problem either, or we have to track, we have to move underwater vehicle with some specific velocity. This is the control objective. So you can see here that I have written two problems, tracking problem and stabilization problem. So what is meaning of stabilization problem? Suppose in between of flow, if I want to control the velocity and I want to stop that underwater vehicle, means Vd equal to 0, means this velocity equal to 0, then that is called a stabilization problem. Tracking means suppose that I have some kind of sinusoidal velocity, some kind of constant velocity, that kind of things I have to track. It is possible to show that in error coordinate, tracking problem is converted into a stabilization problem only. Okay, not always, if difference signal is differentiable. Okay, so here I have just applied the Newton's law to model this system, because I have to just move in one direction. Okay, obviously this is not true if I want to move in any arbitrary direction. Okay, so here you can see that U bar is thruster force that is provided here. So in this underwater vehicle, although this is very, very complicated, but I am telling that I have to move. So I know, I am assuming that this is given to us, and I have to design some kind of force such that I can thruster motor such that I can able to move this underwater vehicle with some specific velocity. So whenever underwater vehicle is move inside the water, so some opposition force comes into picture, that is called drag force, and that is proportional to a square of the velocity. And here you can see that I have written V mod V, because if you want to move in this direction, then drag force is in opposite direction. Suddenly, if you move in backward direction, then direction of the drag velocity, that is in forward direction. So if you simply write V square, then V is, so that drag force is always positive. Due to that reason, I have written V mod V. Means this will also takes care about the direction. And D is some kind of uncertainty, because I cannot able to perfectly model any physical system. So always some gap is there. So I have modeled that gap by D. So what kind of assumption I have? I am assuming that exact profile of D is not known to me, but I am assuming that D is not go beyond some maximum range. Okay, so that is called deterministic framework. Okay, so in that particular framework we are working. So if you see carefully, so this particular system is first order system if I will consider the coordinate of velocity. Okay, and this is non-linear system because V mod V is involved here. Okay, so whenever I have linear system, then I have well-defined design tools. I can talk about the rise time, settling time, or we can also talk in frequency domain that where open loop or closed loop transfer function is going to lie. But whenever we have non-linear system, then at that time I cannot able to distinguish between transient and steady state response. And due to that reason, I need some kind of behavior, some kind of, you can tell that qualitative behavior I can talk. I cannot able to talk about quantitative behavior. In case of linear system, you can talk about quantitative behavior, means rise time, settling time, or these kind of things. And that qualitative behavior is stability, accuracy, and speed of response, robustness, and cost. In this lecture, I am going to cover these 3 points: stability, accuracy, and speed of response, and robustness. Okay, so let us start with stability. Okay, so whenever I want to understand the concept of stability, those who are working on the linear and nonlinear system, you might have seen that whenever we are talking about stability of linear system, at that time we are talking like bonded input, bonded output framework. Okay, but whenever we are going for nonlinear system, at that time we are talking about some other framework, that is either in ISS framework, input to state stability framework, or some kind of Lyapunov framework. So try to understand that how basically that framework comes into picture. So for that we have to understand that why calculus works. Okay, so first we have to understand that how basically calculus is developed. Okay, so if you see the calculus, so calculus is not a new subject. Okay, this is one kind of fancy linear algebra, you can tell. So what happens? During school time, we have already explored the linear algebra. So what basically we are doing, suppose that if I have some kind of slope and that is constant slope, so I can able to calculate the constant slope by dividing the vertical height and this base. Okay, but here you can see that my problem is little more difficult. Problem is like that this slope is now no longer constant, that is varying every time. Okay, so now question comes here that how to calculate the slope. Similar question here, you can see that if I have some kind of rectangle and triangle, then I can able to calculate the area. But suppose that I have some kind of region which is actually here, this is actually varying from point A to B. Then how to calculate the area? And similar story about the length too. Okay, so what is suggestion of Leibniz or Newton? Actually, it is debatable that who has developed calculus till now. So due to that reason, I am not going to that prospect. I am just telling that suppose if I assume that calculus is developed by Newton, so what actually Newton thought that I have to apply linear algebra. So how to apply linear algebra? He was telling that you can go to some point. Suppose I am at this point C. Now you can apply some kind of macroscope. Okay, and what you can do, you can start zooming. So if you do infinite zoom, then what happens? This becomes a straight line. And once this becomes a straight line, then you can apply the linear algebra. Okay, similarly here he was telling that again you can apply macroscope here, and again using macroscope you start zooming. So if I will zoom here at this particular point, then you can see that again area is nothing but the addition of rectangle and triangle. Okay, so what I mean to say that calculus is not a new subject, some kind of linear algebra, fancy linear algebra, where one operation we have to understand, that is how to do zoom. Okay, and so zooming is nothing but here mathematical macroscope. Okay, so I have to define what is meaning of mathematical macroscope, and for that Newton has developed one concept that is called concept of limit. Okay, and if you see the concept of limit, so exactly that is in the same way. So what you can see the definition, first you can see the definition, and after that we are trying to understand the definition. What he is telling that suppose I have x is some independent variable and fx is dependent variable, means you can interpret x as a input and fx as a output. Okay, so he was telling that as x tending towards a, if limit exists L, then for every epsilon there exists a delta such that this condition will satisfy. So if you read this definition, for engineers this definition is quite complicated. Okay, and in first reading, you are not able to understand why for all is written here, why there exists is written here, but try to understand from macroscopic point of view. What is basic idea? So I have already told you that calculus is nothing but some kind of fancy subject. So you have to do zooming. Okay, so if you have to see limit here, then what you have to do? You have to zoom here. So you have to stretch curve here. And if you zoom here, so you can see that this point L is shifted from plus epsilon to minus epsilon. Okay, so what they are telling that now you can do any zoom. So due to that reason, for all, this inverted A is called for all. And if limit exists, then there exists a independent variable L, and again that is going to lie in some range delta. Okay, so you can see that corresponding to epsilon means if epsilon is independent, you can select any kind of zoom. So if you zoom the dependent variable, then what you will get, you are able to get some kind of zooming of the independent variable. Okay, so first you have to zoom the independent variable, and if you will get some kind of bounded region here, then I can tell that there exists a limit. Okay, so and this is here absolute value means distance between this side and this side. Suppose if you have multi-dimensional function, then this absolute value is just converted into norm. Any norm you can take. Norm is nothing but, again, we are talking about the hi-fi idea of distance. Okay, so you can replace by norm. So this is the definition of limit. Continuity is telling that if you see in one dimension, then left hand limit, right hand limit, and limit at this point, if that is equal, then that is something is called continuous. Okay, so if you are able to move from this here to here without lifting your pen, then that is called continuous. So actually limit and continuity go hands to hands if there is no jump or no hole. Okay, that is called hole exception. So similar kind of definition is also available for the continuity. Okay, so what basically limit and continuity is telling, you can see here that what we have done, we have zoomed here output. Y equal to fx. I am telling you can interpret y as a output. And after that, we are trying to see that input is zoomed or not. Okay. And input, there is some hole or not. If there is no hole, then I can tell that something is continuous. So continuity somehow implies the boundedness. It means that now you can interpret something as a machine. You can give some input and you can get some kind of output. If this definition exists, it means that if I will give bounded input locally, then I will get bounded output locally. That is the meaning. And due to that reason, you can see that stability definition is exactly the same. And due to that reason, I have written here continuity to stability. So what they are telling that I have some kind of system, and I have taken that system x dot equal to fx. Okay, what I am assuming, whenever you have force system, you have already designed some kind of control. Okay, and I am assuming initially that control is not function of time. When control is function of time, then I will also give interpretation for that. Okay, only one more channel will increase in that case. So if you solve it, you can see that the solution of this autonomous means there is no extra variable, extra quantity involved here. Okay, so what I am telling that if you give initial condition to this system, then you are going to get xt. Okay, so definition of the stability, for every epsilon, there exists a delta exactly same like previous one. Okay, here I am assuming that equilibrium point x dot equal to fx is the x dot equal to 0 is the equilibrium point. So similar kind of definition. So this kind of definition is adopted by Lyapunov. Okay, and this is called Lyapunov stability. So somehow Lyapunov stability is also the just generalization of bounded input, bounded output. Okay, about the equilibrium point. Okay, that kind of message I want to transmit here. Okay, now let us come to the control part. I will also give another interpretation using just Newton's law that how to understand the stability. So one way, just by zooming, you can able to understand the notion of stability. Okay, now what is meaning of control? I have already told you that whenever I have some objective, then what I have to do, I have to fulfill that objective. Okay, so how to fulfill that objective? I will see the current output and whatever objective I have to fulfill. And after that, I will define the error between these two. Okay, so now what is our aim? I have to minimize that error. Okay, or somehow I have to nullify that error. Okay, so try to understand that I have some process. I have some kind of output and I have some kind of set point. So set point, suppose that if you have to track 0, then that is a stabilization problem. But suppose in this same problem, suppose I have to track VD, then VD is set point and V output of that particular underwater system. So what I am going to do, I am going to calculate the error. And after that, you can see that in PID controller, we have listed 3 blocks. So let us try to understand the interpretation. Why only 3 blocks? Why not 4? Why not 2? Okay. So if you see our decision process, actually control system is fully motivated by our intuition. Okay. So what basically we are doing, whenever I have some kind of situation and I have to take the decision, how basically we are taking decision? We are seeing the present instant, we are seeing the past and future instant. And based on the combination of present, past, and future, we are taking the decision. So similarly, here machine is taking whatever developed by us, we try to implement same kind of methodology to machine also. So for that, we have used the idea of calculus. So what calculus is telling, I have some kind of error signal. This is error evolved with respect to time. So present error is represented by ED. So I have scaled out that error. And after that, we are actually supplying to the system and telling system to suppress this error. Okay. So what I am telling that, suppose I have a small error. So we are giving information that we have to convey our system that error is coming. So due to that reason, sometimes we are scaling up the error. If we have some kind of limitation on the bandwidth of actuator, then actually KP we are keeping low. Okay, so most of time we have to convey our system, please take action as quickly as possible. Due to that reason, we are doing a scaling out. Okay, second thing is that you can see here, you are here. So this is present information. Another thing is past information. Now question is that how to capture the past information. So past information means that is non-local information from here to here. I have started experiment here. And due to that reason, now calculus is giving one way that if you have to calculate the information from here to here, that is nothing but area under here to here. Area under E, T versus T curve. And due to that reason, and how to calculate area using some kind of integral. Okay, and due to that reason, second block comes into picture. Similarly, now our decision might be function of the future, and due to that reason, you can see that future is nothing but the slope at this point. So basically, if you see the PID controller, so that is nothing but 5 different things are involved here: present, past, and future. Time is involved here, and after that, gains are involved. Okay, so based on this 5 information, we are basically designing the control. And based on my knowledge, if you talk about any kind of control system, so that is maximum based on these 5 information only. Okay, sometimes they might based on 1 information and 1 gain, that is okay. But most of time we are just using this 5 information. And due to that reason, I am interpreting that PID controller is universal controller. You can think like this. And after that, whatever controller I am going to design, that is just the subset inside the PID controller. So any controller, if you are going to design, that is nothing but some kind of PID controller only. Only difference is that at that time, this proportional, you might use some kind of nonlinear kind of scaling. In case of this kind of simple integral, you can going to use some kind of complicated integral. In form of this simple derivative, you are going to use some kind of different derivative. So all controller are nothing but the subset. So if you have information of everything, then obviously your controller is very, very good. But nowadays, if you see the system, so most of system is actually working under uncertainty condition. So I cannot assume that I have future information and past information. Okay, in order to design control, because if I rely on the past information, and suppose if I work on network control system, so some hacker will hack my information and they will change. So our control itself destroy our process. And due to that reason, most of time nowadays people are only try to design some kind of controller based on present information. Okay, so this talk, most of time I'm going to talk about how to design means controller based on only present information. I am not assuming that I have past information and future information. So this is the brief overview of the PID controller and how basically PID controller is performing well, because we have all information, you can see. And due to that reason, PID controller is simple and or if you are able to tune the gain, obviously PID controller most of time give you very, very good result. Okay, but what is difficulty? I don't know the gains. I don't know the exact process. Okay, so if some process is running inside closed room, what is my suggestion? You can use the PID controller. Okay, let us try to understand now using this proportional information. I am trying to understand what is meaning of equilibrium point, what is meaning of asymptotic stability, what is meaning of stability. Okay, so what I have done initially, if you remember the first slide, where I have actually taken the information of underwater vehicle, and at that time I have V mod V as a drag force, and I know that whenever some underwater vehicle is going to move inside water, so drag force that comes into picture. So I am interpreting that as a feed forward control. But I am telling that whenever I am going to design some kind of control, I am going to add it in advance, because I know some kind of actually some kind of uncertainty generated by this. So if you design this kind of control, then your closed loop system is now just looks like this. Okay, so now what is our goal? I have to design use such that I can able to maintain V equal to 0. I am going to solve a stabilization problem. Means I have to stop underwater vehicle somewhere. Initially, I am assuming that I have a still water. Means there is no disturbance, that kind of thing. So if you have don't have any disturbance, and if you have just information of present, so I can design this kind of feedback. This is called negative feedback. Negative symbol is here, and we are trying to understand why Kp is greater than 0. Okay, so if you see the closed loop system after substituting this control, that is given like this. Now initially I have some velocity, and what is our aim? I have to make velocity equal to 0. I have to stop. That is the basic idea of a stabilization problem. So let us try to understand just by geometry or using Newton's law. But I am telling that since this underwater vehicle is moving in one direction, due to that reason I have taken real number. Okay, so whenever I have physical system, so whatever input and output we are applying or output getting, that is always some kind of real number, because I don't have any kind of mechanism to measure the complex number. Okay, so whenever we are defining the system, at that time we are assuming our input and output variable both are real. Okay, and since this is one dimensional stabilization problem, and due to that reason I am telling that whatever velocity that is going to generate, that is going to lie on some real line. Velocity may be positive, might be negative. Okay, so now if V is positive, so now you can substitute here. V is positive, and suppose Kp is positive, then what happens? V dot rate of change, that is negative. So V is positive and rate of change is negative. So from Newton's law, system is going to move in direction of rate of change. And due to that reason, you can see that here I have drawn arrow in this direction. Okay, so what happens? That if you are in this side, then you are going to move in this direction. Similarly, if you are in this side, now what happens? Kp is positive, V is negative. So negative, negative, positive. So what happens? Now you are going to move in positive direction. So you are going to again move towards this. Suppose if you are at this point, V equal to 0. So at V equal to 0, you can see that V dot is also 0. So you can apply the Newton's first law, that if you start from some point and if rate of change equal to 0, then you are not going to move. So that is the basic idea of the equilibrium point. Okay, and due to that reason, if you see the current control system or modern control system, so how basically we are defining the equilibrium point? But we are telling that you can convert your n-dimensional system with the vector first order system. Okay, so in place of a scalar, now I have vector, and we are just going to put x dot equal to 0, means rate of change equal to 0. It means that now I have some x you can interpret as a position vector and x dot as a velocity vector. Okay, so I am going to keep velocity vector equal to 0. So basically we are applying just a Newton's first law to understand what is meaning of the equilibrium point. Okay, and whenever we are talking about equilibrium point, at that time we are assuming there is no forcing function. Okay, so either we are talking equilibrium point of autonomous system and non-autonomous system. So non-autonomous systems, at that time I have to apply rate of change equal to 0 for all, like that. Okay, so this is the idea of equilibrium point. It means that using Newton's first law, I can able to talk about the equilibrium point. Okay, and obviously here what we have seen, if there is no disturbance, then all trajectory, whatever that is generated either in this side and this side, that is going to converge towards the equilibrium point. And what we can see, as we are moving towards the zero equilibrium point, what happens? That rate of change is going to decrease. Okay, and if you are very close to this point, and this is unique point, that if you start from here, you are going to stay there. Okay, but all other point, if you start in this space, you are going to move. Okay, and due to that reason, this is called unique point. Okay, and that is equilibrium point. After that, if you start anywhere, so what happens that if you are going to closure, at that time rate of change is going to become slow, and due to that reason, we can tell that I can never able to approach zero, and due to that reason, this kind of convergence is called asymptotic convergence. Okay, so if I have this kind of system, if D is not there, and if I design control based on present information, that is called proportional control. So what happens that if I start anywhere, I can able to converge towards the zero, but I cannot able to converge exactly at the zero. Suppose if I have disturbance, then what happens? Then a story is going to change. Okay, what kind of a story? Now, again, I have real line, but you can see here that this disturbance, I am going to consider the worst case. So actually, as we are moving towards this point, what happens that Kp you can take any value, V, any constant value, V is going to decrease as we are going to move towards this. So once Kp into V, that is dominated over the disturbance, so we can move in this direction. But once Kp multiplied by V is lesser than the disturbance, what happens? Our direction become reverse. And due to that reason, I cannot able to move towards the equilibrium point. So at that time, what happens that whenever I have some kind of disturbance, I can actually lose the asymptotic stability. But at least I can able to give some kind of bondedness. What kind of bondedness? I can give that if I start nearby of equilibrium point, I cannot able to leave this region, because outside of this region, and how basically I have calculated this bond, you can just keep rate of change equal to zero. Okay, so at this boundary rate of change equal to zero, so direction of this actually vector, velocity vector is reverse. So I cannot able to move from this region, and this is called stability. So now you can see that how to define stability. If you actually start nearby of the equilibrium point, you are going to remain nearby of that. Okay, so stability is nothing but bondedness of a state trajectory. What is meaning of asymptotic convergence? What I am telling that in you are not only going to remain inside this ball, you are also going to converge to the zero. Okay, because if you see this slide, so what happens if I start from here, I am going to move in this direction. So I am going to remain inside some ball, and after that I am going to converge here. So I have two requirement, bondedness plus convergence to the origin. Okay, so asymptotic stability tells us little more thing, that bondedness plus convergence to the origin. After that, what is meaning of some exponential stability? I have bonded, but I have rated convergence, means exponentially fast speed, because whenever we are talking about asymptotic stability, we are not talking about a speed of convergence. But in case of exponential stability, we are also talking about the speed of convergence. And due to this reason, if you see the literature, we have first idea of equilibrium point, because that is only one point in a space. If you start from that point, you are going to stay there. So that is very, very unique point. Now what you can do about that point, you can check the behavior. So you are going to talk about stability, asymptotic stability, exponential stability. For linear system, everything is very, very simple. But for nonlinear system, I can only able to talk stability about the equilibrium point. I cannot able to talk about stability of whole system. Okay, because it might possible I have more than one equilibrium point. Now let us come to the another form of stability. Okay, so what now you can do? You can take one cart and keep cart on the ground. Okay, and what I am going to do now, whatever thrust, I am going to keep thrust equal to 0. Okay, so initially I will give some kind of thrust to this cart, and after that I stop it. So what happens that due to some kind of inertia that is going to move, but friction is going to act in opposite direction. And this is the mathematical model. This is nothing but some kind of drive friction. And if you solve this differential equation, it is possible to show that in this particular time, V equal to 0. It means that if I have mass that is very, very high mass, then I have to stop this particular cart that takes longer time. So if you have car, you have truck. So if you apply some kind of force, if you remove the acceleration force, so truck takes longer time to stop. KD is nothing but that is actually based on the quality, friction quality of this road. So that is inversely proportional. Okay, now what you can do, you can perform same experiment inside the water. You can put this cart inside the water. So once you keep cart inside the water, and I am assuming that again, I have some kind of ground and that is filled with water. So again, one more friction force that start acting, that is called viscous friction force. And their value is V square. We have already seen that whenever some underwater vehicle is moving inside water, that is V mod V. So either you can write V mod V or you can write V squared signum V. So signum V, V is greater than 0. So that is positive, V is less than 0, that is negative. Okay, if you solve this kind of differential equation, it is again, this is first order differential equation in coordinate of V. It is possible to show that V equal to 0 as T greater than this time. Again, you can see that what is the difference between these two things. In first case, what happens that this time of convergence is proportional to the or function of the initial velocity, but here that is independent of the initial velocity. It means that you can start with any velocity, that is the maximum time of convergence, and due to that reason, this is called fixed time convergence. Finite time convergence means that is function of the initial condition. So if you are far from the equilibrium point, so it will take more time. But here, even if you are infinite distance from the equilibrium point, it takes maximum this much of time. Why? You can see that one term, that is V square, is dominating here. Okay, so observation is that convergence time is not uniform with respect to initial condition in case of finite time stability. Fixed time stability, convergence time is actually uniform with respect to initial condition. So these two examples are motivating the new kind of stability that is called finite time stability and fixed time stability. Okay, so suppose you have first order system, and if you design control like this using signum function, then it is possible to show that you will get some kind of finite time convergence. I will show this kind of things using Newton's law also in the next slide. Now, one question actually comes in our mind, that is it possible to create some kind of differential equation where time of convergence is independent of this system parameter as well as this velocity. Okay, so suppose that you have some kind of enemy, okay, and you have some kind of defense system, and you want to hit this enemy. So it might possible enemy might be located anywhere, but you have just a very few time to hit that enemy. So at that time, if your time of convergence is function of parameter or initial velocity, then you are not able to hit that. And due to that reason, I need another form of stability that is called arbitrary time stability or free will arbitrary time stability. It means that is independent of the initial condition as well as initial parameter. Okay, so I have done some simulation in MATLAB. So what I have done, I have taken very, very simple system, x dot equal to ut. And after that ut, I have designed based on proportional information. Ut, I have just kept minus xt. You can see that if I start with any initial condition, again, I am going to converge. And this is asymptotic here. After that, I have updated my control like signum xt. Okay, so it is possible to show that xt equal to 0 as t greater than equal to mod x0. So if I start from 2, you can see that within 2 seconds, I'll end up here. If you start from 5, within 5 seconds, I'll end up here. Okay, after that, again, I have actually done more complicated control. And if I apply this kind of control, it is possible to show that if t greater than equal to pi, it means that if I start with any initial condition, so t greater than equal to pi 3.18, so maximum 3.18 second I am going to converge. But I cannot tell that exactly when I will converge, but I can able to give the upper bound, only upper bound. But what is beauty of free will arbitrary time stabilization? You can able to specify the time. You can see here that I have taken initial condition 2 and 5, and I want to design some kind of control. So within 1 second, I can land up to our target or land up to the x equal to 0. Okay. So it is possible to show that using both initial time, exactly at the same time, I can land up. But you can see that control algorithm is more complicated. And that is also depending on the time. Okay. So basically, this is time varying control. Okay. Our whole system is non-autonomous system. Okay. So this is comparison of the 4 different kind of stability. Now let us try to see that why this kind of stability is required. So again, I am going to take example of same system. I am assuming that I have applied control U bar such that whatever damping force that is actually compensated. After that, this is my closed loop system. Now what I am going to do, I am going to understand the on-off control that is based on the on-off control based on the Newton's law. So signum function, you can see that I have defined in some different way. What I am telling that V equal to 0, that is lie from -1 to 1. So I am going to give you the intuition using the Newton's idea only. Okay, so let us try to see here again. If V greater than 0, I am assuming that V belongs to R. I have just one direction of velocity. So in place of X, please interpret here V. Okay, so what I am telling that V, if that is positive, so V greater than 0 means +1. So I have some value of gain. And what I am telling that I have selected gain that is maximum value. This is the absolute value of disturbance. So suppose disturbance is lying between -10 to 10. So I have selected gain that is greater than that. So always if you see V greater than 0, so V dot that is actually is some kind of constant value. Some constant value is going to generate here. Okay. And due to that reason, now direction in this direction, but rate of change is also some kind of number that is never very close to 0. And due to that reason, now you have to move from city A to city B. And if your velocity is finite, even if that is very small, in finite time you are able to move. So due to that reason, if you apply this kind of control, it is possible to show that you can move in finite time. Okay, same kind of information, V1 I have taken and dt sin t I have taken. So within finite time, I will converge here. Okay, after that, what we have done, we have actually done one more simulation. That simulation is like that. At you can see that when V equal to 0, at that time control is switching between +1 and -1. Okay, so high frequency switching. You can see that blue blurred figure appear here. So now if you pass this with low pass filter, then it is possible to show that I can able to reconstruct the disturbance. Okay, so now try to see the interpretation that why I have defined V equal to 0. So if you see the calculus, then we have two different kind of velocity. Here I am assuming V as a position, V dot as a velocity. Okay, in order to give some kind of physical intuition. Okay, so if you see physics, classical physics, then I have two different kind of velocity. One velocity is called average velocity, another velocity is called instantaneous velocity. So this V dot is nothing but instantaneous velocity. Okay, so what basically this system is telling that instantaneous velocity is non-zero. Okay, but average velocity equal to 0. Because after passing through low pass filter, what we have seen that I can able to reconstruct the disturbance. Okay, so if K signum V is passed through low pass filter, at that time I can able to understand what kind of disturbance is actually hitting to this system. So what is interpretation here at this point? That instantaneous velocity is non-zero, but average velocity equal to 0. Okay, and if average velocity equal to 0, then also I cannot able to move. Okay, and due to that reason, at this point we are switching with very high speed, and due to that reason I have defined, and you can see that any kind of disturbance now you can apply by passing through low pass filter. Just here this point that K greater than dt, then you are able to reconstruct the disturbance. Obviously you have to tune the time constant of filter. Okay, then you are able to get this disturbance. So this kind of phenomena we are doing in finite time, because this is finite time convergence. So if initial condition is larger, then you have to wait for large time. So again, one question comes into picture, that is it possible to do estimation of this disturbance in free will time? Answer of this question is yes. Okay, so using this property, this is called on-off control or sliding mode control, classical sliding mode control. So based on this particular law, it is possible to show that I can able to compensate this disturbance, and by passing through low pass filter. So physical interpretation of the average velocity is nothing but you can pass through low pass filter. Okay, so mathematical operation, what we are doing, that is we are talking about average velocity, but physical operation we are passing through low pass filters, because low pass filter is giving the average value. So average value of this equal to t. In this way, I can able to estimate the unknown disturbance. So sliding mode or on-off control is not able to compensate unknown disturbance. Any kind of disturbance you can take. and also they are able to estimate the disturbance. Now, those who are working on power electronics, for that, I have actually designed one on-off control or sliding mode control, you can tell. So what is our objective? I have some kind of LR circuit. This is DC chopper circuit, and I have constant voltage. So, and I have here switch. So by switching control from 0 to 1, what I am going to do? I am going to maintain some kind of a specific current. Okay, this current might be depending on time. Okay, so first what you can do, you can do the mathematical model, just you can apply the KVL. So using KVL, I can get this kind of expression. I hope that you all are already very, well aware about the KVL. And after that, I have to maintain IT equal to ID. Okay, so you can define some kind of error variable or sliding surface, you can tell. Both are exactly the same. Okay, in this problem, this is one-dimensional problem only. And this much of maximum current I can vary. Means I can track between 0 to I max. Any value between V by R. So voltage you can take any value of voltage here, and corresponding R you have to set here. Then I can fix I max. S dot if you take, then this kind of equation. So now what happens? Suppose this is your reference signal, that is ID, and I is here. So I minus ID is negative. Okay, so if S is negative, then you have to switch on this controller. And if you switch on this, basically switch, then this is connected to the voltage. And at that time, it is possible to show that if you maintain this kind of condition, then S is less than 0 and S dot is greater than 0. Okay, so if S is less than 0 and S dot is greater than 0, so you might have seen that I am converging towards S equal to 0. Okay, similar kind of things here. If S greater than 0, at that time, now you have to maintain S dot less than 0. And due to that reason, you have to switch. Means if I am on here, this is ID, but if I am here, then I have to off the voltage part, this voltage part. So I have to switch here. And after that, I can able to maintain this condition. So if overall, if you maintain this kind of condition, and I have to switch between these two, either plus or minus. So I have to design signum S, and I have to design S greater than 0 as a plus 1 and S less than 0 as a minus 1. So you can see here, if you put S greater than equal to 1, so 1 minus 1, so U equal to 0. So if S greater than 0, then UT equal to 0. If S less than 0, so minus 1, that is plus 1. In this way, whenever I have some kind of power electronics circuit, we have to only actually control the time of execution of this particular switch. Okay, so by controlling this, I can able to maintain either a specific voltage or a specific current. So in this way, we are actually implementing sliding mode control or on-off control to the power electronics circuit. Similarly, you can able to implement free will also. Okay. Now, what we have seen in this slide, that if I have just on-off control, then I have to wait for larger time to converge somewhere. I cannot able to control the time of convergence. But what is our goal? Arbitrarily, I want to control. And due to that reason, now I am going to move towards some new definition. Okay, so what I am telling, during simulation, what we found that if right-hand side is time varying, then I can able to talk about some class of system which convergence time can tune in any arbitrary way. What we are telling that whatever control I am going to propose, that is function of time, function of x, tau a you can specify. Whatever time of convergence you want, you can give inside the controller, and gain part you have to give. And you have to make sure that this gain is greater than the order of the system. If you have first order system, then this eta should be greater than 1. If second order system, then that is greater than 2. Similar like that. So this is definition global finite time stability. Meaning of global finite time stability is that x equal to 0 is asymptotically stable, and after that you have to maintain t. And here you can see that time of convergence is function of initial time, initial state u and delta. Okay, but what is meaning of free will arbitrary time? That you can able to tune tau a based on your convenience of your system. Okay, in fixed time stability, you can able to do this job, but what happens exactly? You can be able to tune your time of convergence. That is the limitation. Okay, so this is the definition of free will arbitrary time stable. What we are telling that system is obviously fixed time stable. Fixed time stable means time of convergence is upper bounded by tau max. Okay, tau max is time of convergence. And after that, what we are telling that now tau A, whatever time of convergence you are going to select, that is independent of system parameter or any priori known parameter. Okay, just you have to tune one parameter, even if you have nth order system. And if exactly you are able to tune, then that is called free will strong arbitrary time stable. What happens due to several implementation error, sometimes we are not able to tune exactly, but that is vicinity of that, and due to that reason tau A greater than equal to tau TF. So this is called prescribed time and this is called predefined time. Okay, so arbitrary time stability is actually collection of both. If you see the definition of prescribed time in literature, then they are just talking about convergence up to tau A time. After that, even if disturbance comes into picture, they don't care about that. Means their definition is not extended for whole domain. Okay, but this free will arbitrary time definition is extended for whole domain. That is the difference in these two concepts. Okay, so this is about whenever you are developing some kind of theory, then you have to give some kind of name. Yeah, so that kind of name I have given. So don't worry about that. Let us come to the one very, very simple, because how basically one can develop theory if you are able to understand for a scalar case. So using that scalar case, you can generate the Lyapunov stability, because Lyapunov function is actually mapping from Rn to R. Okay, so just one dimensional result give you the whole idea of n-dimensional result. So that kind of things I'm going to show you here. So what I'm telling that if you have this kind of system, it means that when T0 is lying between T to Tf, and when T is tending towards Tf, at that time you have to switch to 0. Okay, if there is no disturbance. If there is disturbance, then you have to switch to some non-zero value that I will design. Okay, so now you can see that if I solve this equation, then this kind of solution is there. So as T tending towards Tf, so this part is 0 and ln 1. Okay, so log 1 equal to 0. And due to that reason, S is 0, and it is possible to show that as x tending towards 0, so e power x minus 1, that is 0. So x dot also equal to 0. So as T tending towards Tf, it is possible to show that x is 0 and x dot is 0. So by seeing this term, it looks like that might be unbounded because T is tending towards Tf, but that is not the case. So this is 0 by 0 limit form, and it is possible to show that there is also always bounded. Okay, so because when we have designed this kind of controller, then one question obviously came in our mind that this controller is bounded or not, because that is the crucial requirement of any controller. So it is possible to show that there is always bounded. Okay, now this result is only true for a scalar case, but suppose I have nth order system. Okay, so how to actually generalize that result? Okay, so again, I have taken the help of Lyapunov theory. So what Lyapunov theory is telling, suppose you have an n-dimensional system. Okay, and what I am going to define, I am going to define some kind of energy-like function. Okay, so energy-like function that is mapping from Rn to R. So I am telling that I can able to define some kind of Lyapunov function, and if that will satisfy this kind of criteria, okay, then you can see that finally this is nothing but same kind of differential equation as a scalar case that is going to appear. It is possible to show. Okay, detailed proof is available in Automatica paper. Please go through that, those who are interested. It is possible to show now V equal to 0. So in this way, using a scalar case, by seeing a scalar case, you can able to design the Lyapunov stability of free will arbitrary time stability or arbitrary time stability. If you will get this kind of result, then that is a strong arbitrary time stable. If less than equal to, then that is called weak arbitrary time stable. All practical application, we are getting weak arbitrary time stability. Okay. Now, what I have done, whenever you are developing some kind of theory, you have to first give some kind of numerical example. Obviously, after that, you have to apply that theory. So I have constructed some kind of second order system. You can see here that this is actually time varying system, and between T0 to Tf, system dynamics is like this, and after that, that will switch to this. Similarly, x2 like this. So I have actually proposed a very simple Lyapunov function x1 square plus 1 plus gt x2 square. Gt is here, and after that, what we have seen that again similar kind of differential equation comes into picture. Rho dot equal to minus eta e power rho minus 1 e power rho tf minus t. Okay, same like a scalar case. And due to that reason, it is possible to show that x1 and x2 is actually arbitrary time stable. And after that, when t is tending to a tf, that will switch here. So you are already at 0. Okay. And after that, if you are asymptotically or exponentially stable, it means that you are going to remain 0. So that kind of things we have shown here. Okay. Now, let us, what we have seen, that suppose I have some kind of disturbance. Okay. And that disturbance is bounded. So using sliding mode control, I can tell that in finite time, I can able to compensate the disturbance. But I have already told you that in several places, whenever we are designing some kind of disturbance observer or something, I required some kind of free will kind of stability. And due to that reason, I have actually switched like this. Okay. And again, by Lyapunov method, it is possible to show that within fixed time, you can see that similar differential equation I am getting. And it is possible to show that again, if you design this kind of control strategy, so within fixed time, you are able to converge. Within prescribed time, you can tell that whatever time you can specify, arbitrary time, you are able to converge to the equilibrium point. Okay. Obviously, whenever your goal to converge on arbitrary time, then your controller is completed. Okay. Now, this is a story about the first order. Okay. Now, suppose that if you see several practical systems that is of second order. Okay. So some of people here that is working on robotics, they are controlling the motor, and using control of motor, they are trying to control the robot. Okay. So here actuator is nothing but I have electrical actuator that is a motor. Okay, DC motor. And if you see the basic principle of DC motor, so I know that I hope that you all are worrying just for the fresher people I have actually written here. So actually electric motor is nothing but that is able to convert the electrical energy into mechanical energy. And this is the principle. Okay. So what I'm going to do, I'm going to skip this. So whenever I have to design some kind of controller, I have already told you that you have to get some kind of mathematical model. So in order to get mathematical model, what happens? You have two different choices. Either you can develop very, very complicated model. Okay, that will capture a lot of dynamics. Or you go via another way. You can capture simple dynamics, and after that you can apply some kind of robust controller. Robust controller means those kind of controller, if uncertainty is there and if I don't know the uncertainty, but if that is bounded, then that will give similar kind of performance when I have exact knowledge of uncertainty or exact knowledge of system. That is called robust controller. Okay. So since my controller is robust, due to that reason, I can able to do several kind of modification during the mathematical modeling. I can apply several kind of assumptions. So by that kind of assumption, it is possible to show that I can able to model this DC motor. So DC motor is nothing but I have to actually I have to control the robot. So I have to generate some kind of.
Sorry, Sam for disturbing you. Time is up soon, so we have to let some time for discussion, so you can conclude soon your talk.
Okay.
Thank you.
Okay, so I will skip this modeling part. So here you can see that I have second order system. Okay, so for second order system again, you can able to design control like this. Okay, and it is possible to show by Lyapunov analysis, whatever Lyapunov function I have generated, that x1 and x2 0 in any predefined time, whatever time you can set here. Okay, so that is the story. Same kind of things I have actually shown here in simulation, and I have also implemented that on coupled tank system. So coupled tank system, actually I have two configuration. In first configuration, I have to control just water inside this first tank. Okay, and in second configuration, by controlling water in first tank or controlling this pump, I have to control the water in both tank, and it is possible to show that within 50 seconds I can able to do that. Okay, and this is the example of the robotic manipulator, and I have implemented this. Okay, and this is fourth order system. Again, I have designed this kind of control, free will arbitrary time stable control, and it is possible to show that I can able to maintain or Z1, Z2, Z3, Z4 equal to 0 within 6 seconds. Okay, so now it is time to conclude my talk. So in this talk, actually I have started from the fundamental notion of stability. We have reviewed the basic idea of calculus, and using the help of calculus, we trying to understand the notion of stability. And after that, we have seen the all different form of stability. And after that, what we have done, actually, we have also extended this result for the uncertain time system with the help of on-off control or sliding mode control. Okay, and actually now what I have to do, I have to apply this kind of result for several classes of practical system. But in this particular presentation, I haven't shown you any physical implementation. So I have done just implementation on two-tank system or some simple setup. But still, this kind of implementation is open for some kind of power electronic system and lot of different classes of system. And obviously, observer and differentiator design for second order or higher order system based on this concept is actually recently reflected in literature. So you can able to apply that kind of result for several power electronic systems. Okay, and these are some references. And actually more detailed lectures about the control system are available on this link. So I have actually recorded in this COVID period, I have recorded approximately 225 lectures on control system, and that is available on this link. So if you have interest on sliding mode control or fundamental of mathematics, then please go through that. Okay, so with this remark, now actually lecture is in from my side, and now session is open for the question and answer. Okay, so please unmute yourself and ask the question, whatever you want.
Okay, thank you very much, Sam, for a very nice and interesting talk with many information. So audience, if you have questions, please unmute and raise your questions. Ton, you can start now.
Yes. Hello. So,
hello.
Sorry, because of sometimes my internet today it's unstable. So sometimes in and out. So sometimes I may miss some parts. I would like to ask about the free will slide mode control. So maybe you can explain to me briefly more about free will slide mode control. And also the other question is, do you apply this to like motor control? Because I'm working in motor control now. So yeah, thank you.
So thank you for nice question. Actually, I have in our lab, I have one system, two-tank system. Actually, that is provided by Quansar. Okay, so actually I have implemented on that only. So DC motor part I haven't applied till now, because most of time we are working on theory. So after doing one implementation, we are not going for another one. Okay, so it is still, but simulation obviously we have done, and what we have observed that in simulation that is satisfactory. Okay, so please go to the practical implementation to the DC motor part. During simulation, I have observed that response is very exact and very much satisfactory. So I think that similar result you are able to get, whatever that I have shown during the simulation result. Okay, because I have confirmed using a two-tank system, I have already confirmed that I have implemented the free will arbitrary time controller without uncertainty, with uncertainty. After that, free will means sliding mode control. Everything we have implemented. Okay, and one PhD thesis, actually two PhD theses developed with this theoretical idea as well as implementation. Okay, so now you can go for another implementation. And what is difference for sliding mode and arbitrary time sliding mode control? In simple sliding mode control, you are not able to control the time of convergence. Okay, so actually time of convergence is fully function of your initial condition. So you are not able to understand that when you will get your error equal to 0. But in this case, you are able to force your motor such that, suppose that if you want to control the angular velocity, so within t equal to, suppose that 2 seconds you want to control, it is possible to control in 2 seconds. Okay, but whenever you are doing some kind of practical implementation, always system has certain kind of inertia. Okay, so I cannot tell that within 0.1 second I can able to control the motor, because in order to execute the control system command, some time is required. So every system has some kind of inertia, some kind of its own property. Okay, so time of convergence is actually varying from system to system. But if you will able to get some kind of time of convergence, suppose that within 5 seconds I will get. So slowly I can tune for 2 seconds, 3 seconds, and after that I am able to understand that what is the restriction of the system. Similarly, because in case of two-tank system, if you are trying to control means before 30 seconds, then it is not possible. Control is not implementable before 30 seconds. So that kind of things we have observed during the experiment. Okay, so difference is that in sliding mode control, I cannot able to control the time of convergence, but in this case, you are able to control the time of convergence.
Okay, thank you, Sam, for your reply. Is there other questions?
Yeah, I have a question as a presenter.
Okay, go ahead.
Okay, you talked about the finite time convergence, but you gave in your examples, examples on linear systems, right?
Yeah.
Did you have any example on a non-linear system?
Yeah, actually, if you see, then that is not a linear system, because whenever signum function is there, what we have seen that v equal to 0, whenever friction comes into picture, then that is no longer a linear system. Okay, so actually x dot equal to minus k signum x. So that is not a differential equation. That is differential inclusion. Okay, x equal to 0. So that is basically a non-linear system. So it is possible to show that using linear system, I cannot able to get finite time convergence. Always there exists some kind of nonlinear system only. Okay, so now you can complicate that nonlinear system. That is not a problem. Suppose that you have some kind of system like x dot equal to fx plus gx into u. Okay, so what you can do, you can design some kind of control that is a feedback control plus feed forward control. Okay, and obviously you have uncertainty. So what you can do, whatever non-linearity, you can keep that non-linearity in feed forward control, and after that whatever mismatch, that will go to uncertainty, and in this way you can able to implement control for non-linear system also. Particularly if in control non-linear system, all kind of sliding mode control is implementable. Okay, if in control means I am assuming that x dot equal to fx plus gx into u. Okay, fx is non-linear and gx is non-linear. Okay, so for that particular class of system, it is possible to show that I can always able to design some kind of finite time controller, or universal finite time controller is also designed for that particular class of system, same like universal controller.
Yes, the thing is, have you ever had shattering in your results?
So actually now there are 2 points. Okay, so actually if your actuator is very fast, okay, then obviously you can apply on-off controller. Okay, so chattering is actually implementation problem. Okay, but if you have some kind of mechanical actuator, you always get some kind of chattering. But now if you see some kind of literature, so it is possible to modify the classical sliding mode controller by some kind of super twisting control. Okay, so during the definition of predefined time stability, what you can do the modification in that super twisting controller such that you will get the arbitrary time convergence. We have actually done that kind of things, and at that time control become continuous. So using continuous control, so that is continuous in x but discontinuous in t. Okay, so if something is continuous in x, then you are able to remove the chattering. Okay, so that is actually now you have to shift from classical sliding mode to higher order sliding mode control. Then you are able to minimize the chattering. I have already repeated that chattering is actually implementation problem. So completely one cannot able to remove the chattering.
Yeah,
okay, always chattering is there. Okay, because I have to finish some job as quickly as possible. Okay, so that is nothing but some kind of optimal kind of problem. And whenever you are trying to implement some kind of optimal kind of strategy, always you have to do something. You have to switch on and switch off very fastly. And due to that reason, you always have some certain kind of chattering. But you can obviously minimize it by changing discontinuous control by continuous control.
Yeah, so chattering is always a problem, especially if you are
so
designing.
I have told you that means now depending on you, that means if you do complication of the control, then obviously there is no chattering, because your accuracy is 10 power minus 4. So 10 power minus 4 if you apply second order sliding mode control, so then you don't able to see the chattering in your input as well as on output using higher order sliding mode control. But if you are going through first order sliding mode control, obviously you have chattering. So there is no chattering problem. I have already told you that chattering is not problem of sliding mode control. That is problem of implementation. Now, how beautifully you implement your controller, based on that actually your system response or chattering is depending on. Okay. So that is implementation issue. And nowadays, whatever, if you see the literature or if you see the hardware become very, very fast. Okay. So as the speed of hardware is going to increase, then this implementation problem is also going to remove day by day. Because I have seen that in Israel, several systems, they have implemented sliding mode control, first order sliding mode control.
Okay. Okay. There are any other questions?
Yeah.
But if not, I have some questions. The first question is, all of your works are based on model. Do you have idea to extend it to a data-driven framework?
Thank you, Tak. That is very nice question. Actually, what happens that if you see the current literature, then most of time what happens that our system is very, very complicated. Okay. So if our system is very, very complicated, then I have actually input data. I can do experiment and I can collect input data and output data. And based on that, we are going to do some kind of mathematical model. Okay. Mm-hmm. And then now question is that how to apply sliding mode control, because I have input data and output data. So one way that is called Koopman operator. Okay. So what Koopman operator is telling, that suppose that if you have some kind of nonlinear system, and if you lift off that system to finite dimension to infinite dimension, then system looks like linear system. Same like feedback linearization. If you do coordinate transformation, then system comes just like, not exactly like linear system, but in chain of integrator form. And then you are applying the sliding mode controller. So similar kind of things one can think for in case of data-driven system, that they can apply Koopman operator. So applying Koopman operator, system become infinite dimensional. Now, how to design sliding mode control for infinite dimensional system, that we have to take care.
Okay. Very interesting. Yeah.
That one can do model order reduction there. Whenever we are going from finite to infinite, and at that time doing model order reduction, again I have lower order system. Then one can define the classical sliding or predefined sliding.
Yeah. I consider many observation problems. So, what is the benefits of your techniques of arbitrary time stability for observation problems?
Actually, this kind of strategy is very beneficial, particularly for the observation problem. Because in observation problem, what happens that whatever our observer that is running inside the computer. Okay. So at that time, actually, we don't have any kind of limitation on the control value. Okay. So I can apply very, very huge control. Okay. Or very, very huge means updation term or correction term I can apply. So, and here you can see that in all observation problems, somehow we have to force observation error equal to 0 as quickly as possible. So using predefined time, predefined arbitrary time, I can able to force error very quickly.
Okay.
Yeah, so that is the benefit in case of observation.
So the conversion time, right?
Yeah, convergence time one can quickly control.
Okay, so we can easily construct some fit time or finite time estimation.
Yeah, estimator. That is the benefit.
Estimator. Okay. And the last question, so what are the limitations of your technique of arbitrary time stability?
Yeah.
There are some limitations.
Yeah, always, because whenever we try to actually try to get quicker time of convergence, first limitation is that your controller should be actually now that is no longer state dependent. That is now one more thing comes into picture, that is time dependent. So now you have closed loop system is no longer autonomous, that is non-autonomous now. Okay, it means that whatever your feedback mechanism, that is function of time. So you have to take care of that kind of feedback mechanism, because whenever feedback mechanism is function of time, then you have to switch your controller when your job is actually finished. Okay. That is the one limitation. Second limitation is that control is very, very complicated. Okay. Third limitation is that various physical system I have already discussed that they have one time of convergence. Okay, or they have one inertia. So I cannot tell that in arbitrary time I can able to force that error equal to 0. Okay, because suppose that if we take the example of motor system, so motor system has some inertia. So if you apply some signal, then they take some time. Okay, to response that signal. So in arbitrary time always is lower bounded by some number. Okay, so that kind of restriction always there. But theoretically there is no limitation. Okay, theoretically you can do. But in practical implementation, several things.
I see. Okay. Thank you very much.